Okay, good day everyone. Again, welcome back to Fluid Mechanics, another online session. As you remember, the last lecture was about continuity equation in fluid mechanics, and also we have mentioned how to let me hide this. How to how to describe the type of flow, as we mentioned, for the fluid mechanics dynamics. We have different descriptions for the flow in terms of its velocity. Here we said this is the mechanics of fluid dynamic. The dynamics means we have in a motion. Motion means we have to describe whether it's uh, the scientific description of the fluid will be based on different ways. One of the ways is by using the Reynolds number, and we say that we have laminar flow, we have turbulent, and we have transition. And all about Reynolds number when it's less than 2000, that's for pipes, and when it's less than 500 for the open channels in term of, and for turbulent flow for the pipes when the Reynolds number is greater than 4000, or well, that's also for pipes fully flow, and the Reynolds number when it's about greater than 2000, that's for open channels, and the transition one it will be in between. Later we will go deeply for this one, but today we are continuing describing the continuation, or let's say continuity equation, while we have a uniform flow, and that will be based on the followings. Uh, the The continuity equation, let me share with you the note. Here's the notes. For the continuity equation is basically is like this. When we have, for example, when we have a pipe or any channels like this, when it's going like this, we have, this is a pipe. Let's say this is another pipe, and this is another pipe. So we have pipe A, pipe B, pipe C, or in any terms. So there is a point, this is called Y, by the way, this is called Y connection. It's look like Y. This is a Y connection. So the water is going this way and this way and this way. So there is a joint. Now continuity equation is basically telling us that the Q of A, the in, Q in, is equal to Q out. What's the for any system? So if I am focusing on this point, the joint, so what is going in? Q in is QA. So all the flow that is going from A in pipe A and getting this way, it's called QA. That's Q in. And Q out basically is the Q of B and Q of C. So Q out is equal to QB and QC. That's basically the principles of QN. So summation, in another way, there is a summation Q in minus summation Q out is equal to delta Q, and it's equal to 0. That's the continuity equation. What's in, it's going what. So for example, if I have like another junction like this, so this junction when we have Q is going this way, for example, Q1, Q2, and there is a Q3 and Q4 and Q5. So basically, the continuity equation is telling us what? Summation of the Qn, which is Q1 plus Q2, it will be equal to Q3 plus Q4 plus Q5. That's what it's going, that's Q in, and this is Q out with respect to what? To this junction. Now, that's the basic continuity equation. And what we know that the Q, the flow, is usually equal to velocity times A, right? Now, that's in terms of fully average or average velocity. Or as we say, there is, if I have irregular, let's say, like velocity, if velocity is having a profile distribution, it's not regular, so it's equal to velocity times dA. That's based on the A. A is the area that the flow is going in. Okay. And let's go to the example that we have to solve it for you. Here's this example. We have this example, and this example is on your slides. Is telling us that if I have a water like this, waters flow through a pipe. This is a pipe A. So the pipe A is having a flow of 300 kilogram. 300 QA is equal 300 kilogram per second. And as you remember, we said Q is flow volumetric. Volumetric flow. Volumetric means what? Flow rate, which means there will be meter cube per day or per unit of time per second. And we have mass rate, which is denoted by m prime, which is in kilogram per second. The mass rate and the flow rate is the same, but the mass rate usually will be equal to what? Volumetric times the density. As you know, flow here is meter cube per second, and density is kilogram per meter cube. So the result becomes kilogram per second, which means the mass rate. Now, we have to change this mass rate, kilogram per second, to its volumetric rate. So we will say QA, which is equal to 300. And by the way, what's the required? Let me finish this is a double Y. This junction, this pipe connection, that's one of the Y's, and this is another Y, so double Y. So this is a double Y with an average velocity of 3 meters per second through V. So we have V here. This is the VB. So that's VB. This VB is equal to 3 meters per second. And we have VC. VC is here, VC. VC is equal to 2 meters per second. Now, what is the required? The required is to find the velocity at D. How much is that? So it's impossible to find the velocity at D unless you will have the QD. So to find the QD, you have to find the V or velocity at D, you have to find the flow at D. And to find the flow at D, you have to have the flow at B and the flow at C and the flow at A, so that you can say the total inflow is equal to the total outflow. So QA is equal, so here is the key solution. Q at A, which is the inflow, will be equal to Q at B plus Q at C and Q at D. So the key answer is to find this one. To find the Q at D, you have to have the Q at B and the Q at C. You have already QA, but it is not in volumetric, so you have to change it to volumetric one. So Q at A is equal to mass rate at A, which is 300 kilogram per second, times what's the density of water? The density of water is 1,000 kilogram, 1,000, yeah, sorry. We should divide it. Divide by density, because mass rate is equal to Q times density. So the Q rate, volumetric rate, is equal to mass rate divided by density. So here's the mass rate is 300 kilogram per second divided by the density of water, which is 1,000 kilogram per meter cube. So that the kilogram will be cancel out. So the answer is 0.3 meter cube per second. Now we have the volumetric rate, which is equal to 0.3 meter cube per second. Now, so I will put this equation, QA, which is 0.3 meter cube per second, will be equal. What is the QB? QB, by the way, is equal to, for any Q, QB, yeah, QB, Q at B is equal to, Q at B is equal to velocity at B times the area of the B. Area of the B, you know, here's the area of the B. It's a circular shape, and its diameter is what? This is the diameter of B. So because it's a pipe, the area is equal to pi d square over 4, right? Now, so the velocity at B is equal to 3 meter per second. That's the velocity. And the area at B is pi d square. Here's d is 0.25 meter, because it's 250 millimeters. This means 205 meters square divided by 4. Now that's QB. QC, it's also equal to velocity at C times the area at C. The velocity at C is equal to 2 meter per second, and the area at C is pi times the diameter at C is 150 pi 0.15 means meter square over 4. So can you calculate for me these two values? QB. Who's the volunteer now? Hello? Who's the volunteer? Let me pick myself. Arin,
بله دکتر.
can you calculate this for me, QB? And
استمام دکتر.
Barsa, calculate the Q at C. Barsa will calculate QC, and Arin for QOP. Remember, this is the units will become what? Will become meter cube per second. Both. So
دکتر با کیوبیکا کاتا 0.3
exactly another point.
دكتور ومن كردويتي 0.05.
طبعا بوابة the velocity at c is less and the diameter is less, so the result is less. Arin, it's okay? Your answer?
بله دکتر.
So QA, which was how much? 0.3. Here's 0.3 will equal to Q at B, which was 0.147 meter cube per second, plus Q at C, which was 0.035 meter cube per second, plus QD. Now, from this, Q at D will be equal to what will be the value of QD?
والله دكتور حاسبة ملاني يجينا وفتح حسابك عم أخوة
موبايل بنية
بابا موبايل بيه
ماشي.
دكتورة كاتس 0.162.
وين نسوي اشتغل meter cube per second. Now, since we have QD, means this one, so it could be easy to find the velocity at D. How? We will say now for QD, we have QD. As you know, QD is equal to velocity at D times the area at D. So 0.182 is equal to velocity at D, which is the required, times the area at D. The area at D is pi times D square. What's the diameter of the pipe D? It is 250 millimeter, which is 0.25 meter, squaring by 4. So VD, it will be equal to Mani.
Yes, doctor.
Calculate that for me. The V at D. Hello.
والله دكتور بقدر نعطيك دقة.
4 times 0.182 divided by pi, then divided by 0.25 z squared.
دكتور 0.25 سكوير وانيا
بله هو زين كيواتو diameter دي.
دكتور 3.7 3.0 حوس 3.0 حو
3.3 7 like this.
3.0 حو
3.73 right
سي بوينت
unit
حوت صفر حوت دكتور.
like this. Now this is the velocity at d and what it was required. Now that's the application of continuity equation, right? Now we have another question which is here. It is the same as just want you to have focus. Now in this example, look at this example. The velocity of the steady flow means we have A and B is indicated. Determine the velocity at C. So what is the required? It's required to find velocity at C. That's the required. Now I have velocity at A. I have velocity at at B. So we need to know the diameters or the area. So area of A, which is here, is equal to how much? Is equal to 0.1 meters square. And the area at B, at C, is equal to 0.1 meters square also. And the area at B is equal to 0.2 meters square. Now B is greater than A than C. Now, what is the important thing is to find the velocity C, we have to apply the continuity equation. Continuity equation is, where's the flow? It's going from A, that's in, and it's going this way and this way. So we will say Q at A, the flow from A, will be equal to Q for B we have okay, the flow at A equal to the flow at B this way and the flow at C. For flow at A, it's equally Q is equal to V times A, right? So we have the velocity at A, which is 6 meters per second, times, that's the velocity. Area at A is 0.1 meters square, will be equal to Q at B. Here's the Q at B, which is also V times VB times area B. The velocity at B is 2 meters per second. And the area at B is 0.2 meters square. Plus the Q at C is equal to VC, which is I'm looking for its value, times A area at C, which is 0.1 meters square. Now we have only one equation and with one unknown, so VC is equal to Savia tell me VC. Hello? Anybody else? Javier?
هيك دخل
Javier?
في حساب يا كمان.
انت بعد شابنو
دكتور دو كاراتي او بوين دو كاراتي او بوين ياك
أمتى 2 times 0.2 that's 0.4 أمشي 0.6 So 0.6 minus 0.4, 0.2. 0.2
0.2.
divided by 0.2 يعني كذا
Dikkat panza. Doktor.
10
أكاد دو
أما 6 ضرب 0.1 0.6 right
اه
أما 2 ضرب 0.2 0.4 كاتا
اي 0.1
0.6 أنا
دكتور
0.2 0.2 تقسيم 0.1 2 هذا برزق ماشي clear واضحة.
بله.
Okay, we have another question. Here's the question. Here we don't have a pipe. We have a, let's say we have a channel. This channel, the flow is going this way. So the Q. Now what is the required? The 0.5, the depth of the flow here is 0.5. And we are going to this channel, it will be look like this. Okay, so we need to know what is the flow per 1 meter depth, by the way. It's called small q. Q and capital Q, where is the difference between them? Q will be in meter cube per second, which is the total that's covering the whole section. While small q, it will be meter cube per second per meter width for 1 meter depth. So it's less than q, that's why it's noted by small q. Now the question is what is the q through this section? Q is basically equal, as mentioned, q is equal to velocity times the area, right? And since we have a variable velocity, so that's called velocity profile. That's called velocity profile. The profile means here we have velocity, here we have velocity, but the velocity here, u, is equal to 0, since the y, here's the y, equal to 0. But when we have y equal to 0.5, so the velocity is equal 6 times 0.5 squaring, means 6 times 0.25, which is equal to 1.5 meter per second. So here, the velocity at this point is 1.5 meter per second, and here is 0. So that's the velocity profile of this section. Now, what is required? Tell me what is the flow. The flow will be equal to velocity times the area again, but since we don't have a regular shape, we have to use this integration, and we have to use, instead of A, we will use dA, like what we did in our example. Here's the example. You remember this one? Since we have also, this is the velocity profile, and you remember this is the R or Y in our example. So that's given. So what we need to calculate the velocity times the dA. Now dA for our this case, this is the dA. Now for our case, the dA is equal to here. It look like you have a channel. Sorry. We have dA is like that's the dA. This is 1 unit. That's the dy, and that's 1. So dA is equal y okay, y times 1. So dy by dA. Okay, now we have to use dy by 1, dA equal dy by 1. So again, when I say that the Q, the flow is equal to integration of velocity. Velocity is given to me, which is here the velocity, 6y squared is equal to 6y squared times dA is equal to 1 times dy. Now the integration will be over the y from 0 to 0.5. Then that's equal to what? The integration of 6y squared dy. And that will be equal to 6 times, what is the integration of y squared? It's y cubed over 3, right? So it will be from 0 to 0.5. And the answer is 6 times y, which is 0.5, cubed divided by 3. So that's the Q. How much is that? 6 over 3 is 2. 0.5 cubed
0.5 يا دكتور.
or point.
25.
أكيد. أو 0.25 meter cube per second per meter width. So this is the flow through this channel. Okay. Now why it's from 0 to 0.5? Here's the boundary. That's y equal to 0. That's y equal to 0.5. Okay. Any question? Do you have any question?
Das خوش بود دکتر جان.
Okay. Now back to our meeting. I don't know how to stop the meeting. دیارین کپشن نه تو سوری برو presentation available. میتینه کپشن نه تو برو لا خوتانو إن شاء الله كاين بو استوبيكن بس أوي كامنتو إن شاء الله محاضرة داتو زيادة لسر أم بابتا چينا chapter ششو. This way we have done with chapter أمتهاتو. Next we will have another chapter 8 chapter 6